Okay, before we start Unit 4, we're going to review some of the material that you learned in IB Chem 1 about bonding and Lewis structures. Okay, so when we talk about ionic versus covalent bonds, hopefully you're pretty comfortable with these differences. Ionic compounds have a metal and a nonmetal. Covalent compounds have two or more nonmetals. In terms of electrons, ionic compounds transfer electrons, covalent share them. When we talk about how they're actually held together as compounds, ionic compounds are held together by electrostatic attraction between oppositely charged ions. In covalent compounds, we have orbital overlaps. So they're actually sharing electrons, and the nuclei of the two atoms are attracted to the shared electrons. One easy way to distinguish ionic and covalent compounds, besides the composition of the elements, is the electronegativity difference between two elements in a compound. If it's greater than 108, 1.8, we consider it to be ionic. If it's less than or equal to 1.8, we consider it to be covalent. This is just a visual. As you can see in the ionic bond, and I use that term loosely because it's not a true bond, it's just oppositely charged ions that are attracted to each other, whereas in the covalent bond, there's actually shared electron pairs. When we talk about forming an ionic compound, we can use Coulomb's law to understand the force that's holding the ionic lattice together. There's two major factors that affects how strong a lattice is. The first is the charge on the ions. So when we look at sodium chloride versus magnesium chloride, we would see that since a greater charge means a stronger lattice, we would expect that magnesium chloride would have a stronger lattice. And as far as size of ions goes, the larger size ion, so a larger radius, means a weaker lattice. So we would expect that sodium chloride is a weaker lattice than sodium fluoride. Okay, so take a minute, pause, see if you can explain why lithium fluoride has a larger lattice energy than cesium fluoride, and pause and we'll go over the response. Okay, so we can explain this based on the size of the cation. The charge of each ion is the same as is the anion. Because the cesium ion is so much larger than the lithium ion, it contributes to a weaker lattice, and therefore lower lattice energy. When we talk about metallic bonds, we don't talk about these in a great amount of depth. The model that we usually use to talk about metallic bonds is the idea that we have a sea of electrons. So we have electrostatic attractions that are occurring between positively charged metal ions and delocalized electrons. Delocalized means relatively free moving. When we compare the physical properties of ionic, covalent, and metallic compounds, if you're asked to do this, the easiest way to do it is to think about common ionic, covalent, and metallic compounds. So for ionic, you could think about salt. For covalent compounds, you could think about candle wax or water or carbon dioxide. And for metallic compounds, you could think about copper wire. So this compares their melting and boiling points. It is very hard to melt or boil an ionic compound. You are not going to melt salt easily, okay? So they have very high melting and boiling points. There's a lot of variation in covalent compounds, but relatively compared to the others, they're low, and metallic compounds have high melting and boiling points. Volatility refers to the ease with which something is evaporated. So for ionic compounds, it's near zero. For metallic compounds, it's also near zero for most, with mercury being a pretty notable exception, and covalent compounds are relatively high. As far as conductivity goes, metals are great conductors, and covalent compounds tend to be insulators. Ionic compounds have no conductivity as a solid because they're too brittle, but when they're dissolved in water or molten, they're very conductive. Okay, now this is going to be a quick review of Lewis dot structures. We'll go over some of this in class as well, and I encourage you, if you've forgotten how to do this, to look in the textbook at the worked examples in Chapter 4, because that would be really helpful to you. General rules for how to do this. First, we're going to count the total number of valence electrons in the molecule. Carbon has 4, and each oxygen has 6, so we have a total of 16. Next, we want to arrange the atoms spatially. Typically, we're going to put the least electronegative atom in the center, except bear in mind hydrogen can never be a central atom because it only makes one bond. Now, one helpful thing that you can do when you figure out how many bonds to put between elements is to consider how many electrons each atom needs to be stable. Remember that we're trying to satisfy the octet rule, so every atom is trying to get 8 electrons. Carbon needs 4 electrons, so it's going to tend to make 4 bonds. Oxygen needs 2, so it will usually make 2 bonds. This isn't a hard and fast rule, but it's a good place to start. Now, try drawing your structure. So if we followed these rules so far, it would look like this. Now we're going to add lone pairs as needed to give each atom a full octet. So we would add 2 lone pairs to each oxygen, which would bring us up to a total of 16 electrons. So let's check. Have we used the correct total number of electrons? Well, once we add in those lone pairs, we'll have 16, so yes. And we need to check that each atom has the octet rule satisfied. Note that hydrogen will only need 2 electrons and boron only needs 6. But we don't have either of those here, so each of them will have 8 electrons, again, once the lone pairs are added in. If both of those are correct, you're done. If not, you're going to need to adjust the number of bonds between atoms and therefore the lone pairs to make sure that each atom is satisfied without using too many or too few valence electrons. Now, once we've done this, and again, we'll practice that, so if you're not comfortable just yet, that's okay. We're going to be able to determine the molecular shape of a covalent molecule using VSEPR theory. That's short for valence shell electron pair repulsion theory, which kind of makes sense, right? We're talking about the valence electrons, they repel each other, and that determines the shape. The molecular geometry, or the shape, is determined based on 2 things. First, the number of electron domains. So that's the total number of bonded groups and lone pairs around a central atom. When we talk about the number of electron domains, we refer to that as the electron domain geometry. And 2, the presence or absence of lone pairs has special significance. Okay, now if we have 2 atoms and that's it, there's only one thing they can be. They have to be linear. Okay, it's the only option. We can't have any kind of crazy curved bond. If we have 3 atoms, though, we have 2 other options. Now, when we look at carbon dioxide, we see that there's no lone pairs in the central atom. Okay, so this is going to be linear, and it'll have a bond angle of 180 degrees. Water, on the other hand, has 2 lone pairs in the central atom, and these are going to repel the bonded pairs. Okay, so the bond angle here would be 104.5 between the 2 bonds. When we have 3 atoms attached to a central atom, again we see differences based on the presence or absence of lone pairs. The first molecule has no lone pairs in the central atom, so the furthest distance that these bonds can be away from each other is 120 degrees. Okay? If there is a lone pair, however, this becomes a trigonal pyramid, where the bond angle is about 107 degrees. Now, when we have 4 atoms attached to a central atom, typically this is a tetrahedral with bond angles of 109.5. Now, if we think back to the bond angles that we've previously looked at for bent and trigonal pyramid, we notice that they're kind of similar, 104.5, 107, and 109.5. So this is pretty significant. This is because each of these has a tetrahedral electron domain geometry. So that means 4 things around a central atom. In water, it had 2 bonded groups and 2 lone pairs, 4 things, tetrahedral electron domain geometry. And in trigonal pyramid, it had 3 bonded groups and 1 lone pair, again, a tetrahedral electron domain geometry. Because those lone pairs are slightly more repulsive than bonded pairs, every added lone pair will make the bond angle slightly smaller. So in the tetrahedral, when there's no lone pairs, it's 109.5. In the trigonal pyramid, when there's 1 lone pair, it goes down to 107, and then when there's 2 in the bent molecule, it goes to 104.5. Now, we have something called an expanded octet that can occur. Okay, you see phosphorus here has 5 bonds, and that seems weird because we've talked about the octet rule. Atoms in the 3rd period or below, however, can have more than 8 electrons. We can explain this by the presence of d orbitals in the 3rd energy level, so atoms can expand into the d orbitals of the 3rd energy level if necessary. So this is a trigonal bipyramid. If you think about those 3 chlorines in the center as forming a flat plane, there's a pyramid pointing upwards and a pyramid pointing downwards, and I'll show you some models of this in class to help too. We have bond angles of both 90 and 120 degrees. And finally, when we have 6 atoms bonded to a central atom, this is called an octahedral. Seems weird, right? 6 atoms and we call it an octahedral, but if you were to fill that shape out, it would have 8 sides, and the bond angle is 90 degrees. So last but not least, we want to talk about bonds. We need to talk sometimes about bond strength and bond length. If I have generally more bonds between two atoms, it's stronger, so it takes more energy to break the bond, and it's shorter because there's a greater degree of overlap and shared electrons. They're going to be held together more closely. Okay, try some of the practice, bring your questions to class, and we'll go from there.